Okay, so let's continue our section. Please.
Thanks a lot. Thanks a lot for waiting to the Friday afternoon. So I talk a little bit slower in the morning time, so the following will be a lot of the details, techniques. Most of them have been published. Some of them are new, haven't published it yet. But you can either reference our papers later on, or they're new, so we can have more discussions. So we can further improve our architectures. So previously, I tried to spend time to introduce thoroughly on our design concept. The previous designs was for the single layers majority to explain how the design works. We also trying to extend the works to the multi-level designs, and here is the example. This is in hybrid spiking multi-layer self-learning neuromorphic systems. In fact, in recent years, we switching to the spiking based for power efficiency consideration. Multi-layers, it's essential to extend the system to multi-layers in order to extend the scale of the design and then process bigger amount of the data. Well, for those designs, we emphasize the self-learnings. Major reason affects process variations is noise. So at lunchtime, actually, we had discussion with the TSMC Dr. Chen, and the process variations and endurance in those device intrinsic characters will be very critical in our design. So we propose this multi-layer kind of illustration structures. Well, in conventional backpropagation equations, again, the change of the weight will be determined by the difference of the target and calculated results. Well, in the modified equations, again, we change that to sign functionalities. Magnitude will be decided by pre-designed, kind of a pre-designed parameters, and will not be determined based on this calculation, will not be embedded into the calculation. And here is in structures. I use two-layer designs to illustrate the structure. So we start with the randomly initialize the weights. Assume the situation is, okay, we have a Memristor crossbar already fabricated. We have randomized the initialize the weight. Well, training start with the feed-forward structures. We supply input. Input will go through the two layers till the end of the structures. And then we are able to calculate the error sign of the output neurons, as I illustrate over here. The sign function, the results actually will be used as error mapping to determine the training configurations, meaning the direction of the currents, the amplitude of currents, and so on and so forth. So this is for the second layers. And we also can apply the programming process using according signs and calculated to train the first layers. So this is train the second layer first and then used to the first layers. Our paper were published on the date 2017 explain how to control the sign functionalities during the training process over here. Well, here is kind of the evaluations. For all the spike simulation based works, we can only demonstrate the small scale applications, and this is again very small scale applications. As you can see, the network size is very small. First, input layer is 32, middle layer is 10, and the upper layer is 6 for those examples. While we have 600 training set size and testing size is 200. Well, over here I show you some kind of results for those networks. The y-axis is average filler errors, and the x-axis is the data sets. For each set of data sets, we have the dark blue represent conventional two-layer neural networks. As you can see, it's always present ideal training. The situations. They always have the lowest failure error rate. Two-layer spiking-based systems represented by kind of light green bar over here, and the one-layer spiking-based systems represented by the yellowish bar over here. So more levels in the networks can represent more knowledge of the information, therefore have a better recognition rate. And over here, those numbers represent the training epochs, meaning how many iterations to make training converged. So as you can see, two-layer design usually requires more iterations to get converged in order to learn those knowledges. As I said, our conception is to talk about we're trying to trace what is the optimal designs. For IFCs, x-axis is the pause numbers. So when we increase the pauses, of course the failure rate kind of decreases as those examples shows. So again, the required pauses is related to the complexity of the applications. For a simple case like a cancer, like the binary digits over here, small number of pauses is sufficient because your input data is binary format. There's no gray levels, and output is quite simple, only 6 digits. Well, for some more complex applications, so we have to extend the output pauses. This is kind of expectable. We also trying to evaluate the impact of the process variations. So x-axis on the left figures shows the deviation of the process variations. The y-axis again shows the average failure error rate. For each applications, the pair shows before and after applying the self-learnings. So the essential information we're trying to deliver is for Memristor crossbar structures, the self-learning is necessary. In fact, this work is not so obvious, but some other works shows is the better approach probably is to program the Memristors to some initial values. The initial values based on the theoretical calculations. Okay, because the programming will generate some variations, so we can do some online trainings to overcome or compensate the impact of the variations or even the defects. That is what we believe the better approach. Another advantage of such an approach, in fact, is by doing this, the epochs for online training can be significantly reduced because the starting point already very close to the optimal setups. Okay, so that's probably more practical. And another observation we have, in fact, is during the circuit designs, we in fact summarize the noises or the variations to the static and dynamic. Dynamic noises comparably is harder to overcome because it's random and it occurs during the operation. So system level or algorithm level compensation skills is really hard to cover, those variations. The process variations, for instance, as I'm going to discuss very soon, since those are critical, those are statistics, and a lot of the patterns can be traced. So those, in fact, we can start, handle that from the higher levels. So the right part shows the training speed. Again, when the system have more variations, training will take longer time. We say, Well, our labs actually since 2015 since starting the fabrication of the chips. Majority of the measurement results actually for these designs. For the new designs, for example, the level-based designs, the one integrated with the RMs, and also we have something submitted early this year. We're still waiting for the permissions to present and publish this. to quickly summarize this, so far we have 4 or 5 Neuro-Chips spike and level-based, and the majority of the fabrications were sponsored by United Air Force Research Labs. Well, so far I actually complete my design concept part, and following I'm going to talk some detailed challenges and issues we face. We propose some solutions. They might not be the best, and I think discussions are well welcome. First caveat I want to show you, in fact, is the reliabilities. So this is a very simple illustrations. Essentially, for a network, the variability means the weight over there is kind of diverse from the ideal weight, where there could be some defect. It could be on or off defect. It's stuck at the high resistance level or lower resistance levels. At the upper neuron, in this simple examples, it's essentially collected the data and weighted input data. So the defect in the weights could significantly affect the final calculation results and make following calculation completely wrong. So we actually do the semi-slow simulations for this for a 2-layer network used for Memristor recognizations. The x-axis shows the defect percentage, and the y-axis shows normalized accuracy. So what I meant is, ideal case, assume the accuracy, the real accuracy about 96-97%. Assume this is 1. Okay, and then we intentionally inject the defects to the system and say, again, we doing Memristor testings and see the recognition accuracy. Of course, depends on how do we inject the defects. The accuracy changes in the range, but generally speaking, the accuracy degrades quite significantly. This is one observation. Another observation, in fact, is for each testing node, you can see this range is also very, very big. For some cases, the accuracy, I wouldn't say it's tolerable, but not that bad. Compared to this is close to 20%, meaning the system is completely destroyed. So we introduced the concept of the weight significance. Okay, to talk about the weight significance, let me use only 1 layer networks. It's more obvious to show the situations. What I really want to show here is for the networks, the contribution of those weights are not equal. Some weights contribute more to the final results, and some weights have less impact on the final calculation results. For example, this is one level. You can see that the color over here to show impact of the defects on the different weights. And we use Memristor data as an example. So, for instance, for all Memristor cases, the corners, the surroundings, since it doesn't contain the features of characters, so those are not important at all. Okay. The center part show the features, so it's illustrate the knowledge we trying to extract. So the weights of these regions is more important. This is kind of easy to understand. When we extend to multi-level networks, okay, the illustration will become not so obvious. But essentially, the concept of some weights are important than the others will remain valid. Okay, so theoretical-wise, we can try to classify the significance by use mathematics. Essentially, we can try to analyze this, the derivatives of the final loss function nowadays, final loss function over the derivative of the weight. Okay, and this can represent significance. So in those structures, we simply set one threshold. Whenever it's exceeding the threshold, we say, okay, this weight contributes more. And if it's less than the threshold, it contributes less. So if you're doing this, and we doing again the similar analysis for insignificant weights, even we disturb it quite, you can see overall system accuracy doesn't change much. But for the significant weights, it has less tolerance on the defects. Okay, so this is the situation. Well, how do we overcome this? For here, we present very simple structures, rescue the network retraining. Essentially, for crossbar arrays from memory systems, well, we assume that when we have the crossbar fabricated, tested, we are able to identify the defects, either stuck on or stuck off. So initially, generally the network can be trained theoretically. Well, for each single mappings, we can do retrain. During the retrains, we can identify the defects. Okay. We started from ideal mappings and then force the defected locations to be either high or lows, and then we do the retrain. In fact, we find this methodology quite effective because the network itself has some self-sustained capabilities. Okay, many of the times they're able to recover itself. So the flow, in fact, is retraining is kind of theoretical structures. So the purple two steps were inserted as a retrain processes. Well, for the significant weights, if many of them were defected, we probably have to introduce some redundancy to recover it. I think if you're ever doing the memory designs, the concept is quite simple and straightforward. Well, but say the result is quite good. So before retrainings, this is the trend we just represented. And after retrainings, you can say even the defect percentage up to 20%, the overall system's accuracy-wise is close to normalized 100%. And here I showed weight distributions. What I really represent through the two figures, in fact, previously majority weights are distributing in this way. And now, after retrains, the two sides represent the defected, like either stuck on or stuck off. Okay, we force those weights to be 1 or 0 and so on and so forth, positive, negative ones, and then retweak the weights to obtain the functionality. We also evaluated the resiliencies of the significant and insignificant weight. Again, this results already been seen. For insignificant weight, as you can see, the degradation is much slower than significant weights, and of course, it's easy to get recovered. Redundancy part evaluation, more detailed evaluation over here is shown. I think the key design over here is how do you identify the most critical significant weight and pick the top one to get replaced. Okay, so again, remember we have this theoretical criteria over here. We in fact use this to ranking the significance of each weight and to determine which one to pick first and second, so on so first. Well, a quick summary on the reliability part. Defect rescue design methodology is proposed. The goal is to restore the accuracy loss induced by random defects. While other methodologies trying to integrate three major components. First, weight significant. Second, retraining algorithms. And third is remapping processes. Another information I didn't present over here, but I think we can discuss is my concept is second of the defect is kind of we catalog as a static wise. So those static defects or variabilities, system level approach can handle those very well because they know what happens over here. We recently have a work accepted by the ICCAT. I do not have a slides ready to present over here. That one is because of the weight shifting, the resistance shifting on memory technologies. Basically, it's meaning that when you access the devices, the resistance will be get slowly drift from its original values, right? That is heavily related to the operation conditions, and those kind of very random, into variations. What we find is it's hard to cover by system level. So the lower level, like circuit structures, will be necessary. And we had some initial results and will be present on ISACAD this year. Yes. Yes. We do not narrow the conductance. Yeah. You mean for this reliability or for the? So we actually did not evaluate at the beginning. We just say, okay, based on the measurement result, we can easily tell the defect. So this would only focus for the defect that cannot be programmed or cannot be trained completely. So for the cases that during the programming is changed slowly or faster, that variability will be covered by the self-learning itself. Okay. Another thing I want to talk is limited precisions. So we work with HP Labs and other companies. Many other collaborators, in fact, are working on memory and storage. Okay, they are not working on the Neuromorphic computings. They're more interested in design memory devices supply 2 values or 4 values or up to 8 values, multi-level memory cells. Okay, they do not provide really analog levels and so on and so forth. So we're trying to make those memory arrays working for the Neuromorphic designs, and we say, okay, how can we do this? So in this work, we try to analyze the quantization processes. Essentially, how do we optimize that? How do we optimize how do we mapping the floating point weights in original algorithm level to 1 level weights in the Neuromorphic computing systems? Okay. What's very obvious is floating weights. If we simply map either to high or low, it shows quite significant informations. And as you can see for LANET, it's kind of a CNN structures and trained for MNIST. It's still very simple examples. So floating point weights, it can obtain 99% of accuracy. With 1 level weight mappings, the accuracy dramatically dropped to 90%. It's already close to and useful. Well, it's kind of a major challenge, especially with trying to leverage the existing memory technologies. So in this work, we propose classification, accuracy improving methodologies, including 3 parts: the distribution-aware quantization, quantization regularization, and bias tuning. First of all, the distribution-aware quantization. So for quantization, usually what people do is set and threshold for like 1 level precision, like resistance high and low. Set the bar and say, okay, whenever higher this bar, then this 1, lower than this bar, then 0. Okay. Well, what we find during the analysis is the learned weight for different layers, in fact, are different. So that's looking at those figures, the blue bar part. The blue bar shows the weight distributions of the theoretical training results. As you can see, first you can see x-axis, the range for different layers, convolution 1, convolution 2, inner product 1, inner product 2, they are different, right? The shape are different. So what we propose, in fact, is 3D quantizations for different layers. We shall optimize the selection of the weight instead of to use one uniform selections to all the layers. Okay, so if you're doing this, I mean for laminate again, theoretical 99%, traditional quantization 90%. By just doing this distribution-aware quantizations, we can recover to 98%. Of course, this is also because the network is so simple. Quantization regularization (QOR) is because the previous distribution-aware quantization is used for quantization processes. Essentially, say, okay, for the trainings, we decide this, and then we got these distributions, and based on distributions, we picked the optimized the quantization values for each layer, and that's it. The training part was not really considered, and the quantization regularization is kind of a really algorithm level to consider or optimize the training part. So, for network training processes, usually we add some arrow functionalities to constrain the shape of the trained weight matrix. So L1 norm regularization is kind of widely adopted. L1 normalization, I mean, this shows the arrow normalizations. So L1 is represented by the red curve. So as you can see, it's essentially say bigger weight contribute bigger arrows first, and since the trend, the slope is very steep over here. So L1 is kind of, the intent of L1 is generate more zeros. Okay. Well, L2 norm regularization is used the weight square to criticize the arrows. So it's represented by this red curve. The red curve is slope-wise, it's steep when the weight is big, but kind of get slowed down when the weight is small. So L2 is trying to get more weight crowded in the small values. Okay. Well, what we're trying to do is, since for memory-based memory crossbar arrays, we only have like one value available or two value availables. So it's indicating that we're trying to constrain the training result to some discrete values. So we proposed such kind of arrow functionalities. So the blue curve shows the trend, and its result more weights are crowded on those discrete values. And of course, those values can be defined by our designer. Well, for doing this, this actually the orange or the green bar shows the QR. So you can see after utilizing our arrow functionality, and the distribution will become strict to those discrete levels, and this actually satisfies our results. By only using QRs, we can recover the accuracy to 96-97%. And of course, later on, I'm going to show you how to combine them together. Well, another structure we proposed for this is the bias tunings. So consider the deviations, the weight deviations, overall results, the deviation at outputs, right? It's kind of easy to understand. Well, the major difficulty of the harm is the deviation, the delta yj, it's not only affect these layers. For mapping layers, or the system on chips, it's going to propagate through layers. Okay, so the impacts is kind of accumulated. And this is the critical part. So we try to solve the impact at the local on this layer only. So we propose the bias tuning structures. Essentially, we try to tune the B using each layers to compensate the delta yj or eliminate the delta yj. so it's not going to be propagated to the following layers. That's kind of the basic concept. So circuit design-wise, we do weight quantizations, and determined by the measurement results, we freeze the weight and tune the bias of it in trying to improve the performance of the system. So let me give some evaluation results. So for the evaluations, we tried different networks, the multi-layer perception MRP, and CNN structures. We tried MNIST and the CypherTin. MNIST is, we talked about many times handwritten digits in white and black. And CypherTin is colorful images, so it's more complex. Well, here is the network configurations. For each layers, the configurations over here. So for each evaluations, we try a combination of different technologies. EQ represent distribution-aware quantization, QR represent quantization regularization, and BT represent the bias tunings. We start with only apply one technologies, and then combine two, and combine three altogether. For simple networks and simple data sets like MLP on MNIST, one scheme or at least two can try to cover the impact, as I show over here. But as the data set and network becomes more complex, for the CNN on the CypherTin data set is quite critical. As you can see, the baseline is completely damaged, and the system cannot work. Apply one technology, cannot recover that, but performance is still far from satisfactory. So 2 to 3 methodologies will be better for the requirement. And another observation is, in fact, the quantization QR. Sorry, I couldn't. The quantization regularization schemes is very critical. It's essentially using the system level training method to make its converge to discrete values. How many labels? No, for this is only 0 and positive, negative 3 levels. Yes. And this is kind of an illustration. I know it's kind of hard to say, but the expectation is the first line, for instance, is show learned filters, and the second line shows the learned filters for vulnerable situation. So the shape and colors represent kind of knowledge learned. The closer the two parts are, meaning the better information maintenance, and you can see that it's quite close, but it's still difference because we only have a one level over here. Bias tunings expect to help to elevate variations, so we need analysis over here. Essentially, without bias tunings, again, when we inject some noises, the system kind of degrade really soon. And bias tunings can then compensate certain of this. So it's kind of related to the reliability again. Okay. So this work we published on the SPDAC early this year. A lot of details can be found in the paper. We recently had a paper published on the DAC 2017 on the scalabilities. The author of this work and the limited precision actually the same. I didn't include this part in the slides, but I can quickly go over this. So, situation we face in Memristor-based or Algorithm-based neuromorphic design is from system level, the network becomes larger and larger. So when I talk about the larger, it's not only more layers, but for each layer, the size, the networks grows really fast. Okay, crossbar array usually, at current stage, majority of physical crossbar arrays I can access is very small. We talk about 100 by 100. We talk about 64 by 64. Compared to those numbers, it's extremely small. So in implementations, we have to partition a large array into several, Memristor crossbar arrays and putting them together. Okay, so the efficiency of the implementation becomes critical. And another observation on a higher level, in fact, is though the array here is huge, many of the weights are zeros, or the value is extremely small and doesn't, even remove that, it doesn't hurt system performance a lot. So we propose called Scissor framework. It has two goals. Okay, it has two components corresponding to goals. Rank clipping is trying to reduce crossbar area occupation. So meaning we're trying to reduce the weight matrix size, and then we can reduce the utilization of the crossbar arrays. And then we have to handle the communications across between crossbars, right? So group connection deletions is used to reduce the routing conjunctions. Okay. So in this ways, our expectation is in large crossbar arrays can be partitioned and applied to minimum number of the large network can be partitioned and applied to minimum number of the crossbar arrays. Well, okay. So low rank for the rank clippings, we apply the low rank approximation LRA. I guess many of you have heard about the low rank approximation LRAs. The concept is to approximate a large matrix using the product of a smaller matrix. Okay. So, for example, I show a simple illustration for the simple component analysis. This is the data sets we're interested. Originally, it's in a three-dimensional space, or 11 those dimensional spaces. So if we are able to create and find PC1 and PC2 mapping on this surfaces, and then it can be represented by two-dimensional matrix, right? So it becomes simpler. So when we're doing the reduced dimension of weight matrix in large, so when we're doing this, meaning a large weight matrix can be approximated by two lower rank matrices. So for instance, W originally is in the dimension of n times m. Both n and m are pretty large. And then we can reduce represented by U and V transpose. So U is in the dimension of n times k, and V is k times m. So if we are able to make k very, very small, so the the W can be realized by two of these, and each of them are very small. So and of course during this we have some approximation structures. So W wave could be a little different from W. So we have to trace the impact on the overall system accuracy or performance. So during these reconstructions, we use this functionality to represent the reconstruction arrow. In our designs, rank clipping, we integrate the PCA into the training processes. So as you can see, all we're trying to do is not like separate the whole processes, as individual actions. We always trying to, improve the training processes so the trained networks will be easy to implement on members of crossbar arrays. So as the algorithm show over here, for each layers, we do the PCAs during the trainings, and then to examine reconstruction arrows and compare with the tolerable clipping arrows. So the bottom part is kind of, again, simple animations to show what we're trying to do. Here is the original weight matrix in large size. We try to represent it into two arrays, U and V's. And during the training processes, we tend to remove the weights in rows or columns through by controlling the arrow functionalities. So in this way, essentially V is in this shape, and U in this shape and V in this shape. As you can see, the dimension of each of them can be much smaller than the original W over here. Okay, and the sum of them is also much smaller than the original W over here. For rank clipping, we do the analysis on its impact on the systems. Okay, so here I use two databases, two networks. LANet for MNIST, simple networks for MNIST, ConfNet for the CyberNet. And for each configurations, we try original methodologies. Directly LRAs, meaning we train the networks by using original methodologies, and then we apply the LRA, the PCA, for instance, in number methodologies, and that's it. And then we say how is the accuracy and what is obtained U and V's for each layers. We also showed rank clipping, meaning we embedded the LRA into the training processes and see how is the results. Okay, so for either of them, obviously you can see the accuracy recovery, because LRA will create some errors, right? The W wave is different from W. So this difference will kind of eventually degrade the system performance. But since we embedded the PCAs into the training processes and keep tracking the system performance, so the accuracy is recovered very close to the original design. This difference actually can be taken as random errors, right? Well, talking about the rank, for all these layers, as you can see, the directly LRA and the rank clippings are three similar rank K on each layer, and same over here, meaning the implementation cost is close or exactly the same for the ideal expectations. Okay. Another general question usually I will be asked is how fast if you're doing this in trainings. Because training usually takes a huge time, especially when the network size is huge. So we show the trend over here. Okay, so in this one, first the black curve shows the accuracy of the systems through the training iterations. We start with network trained under ideal situations, so the accuracy remain high, and as you can see, it continually remain high during the entire iterations. Well, for different layers, first of all, the green curve represents fully connect layers. So if you do some neural networks, you probably know that fully connection layers has a large amount of connections, but usually majority of the widths are not very significant. That's why you can see that the rank drop is very quick for fully connection layers, and eventually it gets saturated. The rank ratios can be really, really low. Okay. The convolution layers, because the functionality of a convolution layer in NN is to capture the features. So usually convolution layers, the possible sparsity rate is not as high as the fully connection layers. So you can say it drops, but wouldn't be as slow as the fully connected layers. But eventually it also gets saturated for the case being evaluated. So it's generate, it requires more iterations because each number over here has 2 times 500. So generally speaking, we need about 20,000 more iterations for training. It's still very high cost. And many machine learning, many people's, I have to say, they do not like the idea. But for other situations, in fact, we have to handle the hardware constraints that usually software people do not think a lot. And then I think this is, well, we have to sacrifice either here or there. So, yes. Oh, so once we finish the rank clippings, we reduce the size of the networks and have those in U and V's, right? We are able to map them into different crossbar arrays. Next question, in fact, is the communication cost. So imagine you have 4 crossbar arrays. Each of them have 20 connections, and then 20 from this to this one to this one to this one. So overall, the communication requirement is still significant. The group connection deletion methodology we propose here is trying to handle the case. So the observation is, okay, instead of talking about connection cutting itself, we think about the group, the columns groups. So the column groups, if in one row or one column, all weights are zeros, then basically the calculation of this row of columns is not important. Then we can actually delete the corresponding connections, right? So what we do is on the arrow functionalities, we add true plus O functionality. Remember I talked about the true plus O L2 norm, and then L1 norm, and overall L1 norm is trying to get more zeros. But very important is we do row level group plus O and column level group plus O. So what we're trying to do is remove the weights on entire rows or entire columns, not one single random weight. Okay. So here actually is our results. Again, x-axis is training iterations. This is the result for LUNET. And y-axis could be accuracy and also the deleted routing wires. Again, for really dark back curves shows the accuracy kind of fluctuated but still remain high. The pre-connect layers, the green and purple ones, as you can see, since pre-connection layers can be really sparse, we get more chance to remove unnecessary column rows, and then we get more chance to cut off the routings. Convolutional layers, unfortunately, it's maintaining more information, so the impact is not as significant. I do expect it, extending the iterations, we might get saturation somewhere, but it's really could take really long. Again, we usually like to get some illustrations to show the impact over here. Say this is a fully connected layers, and I use U and V's. I think it's UV situations, and each rectangles to represent one Memristor crossbar array mappings. So as you can see, for instance, here and here, it's almost empty because our schemes kind of remove majority of the connections. So in real implementations, we might combine them completely. And this is the 2 million structures. So you say we tend to remove entire rows. I will see many entire columns in the structures over here. So this is how we, improve the routings and also improve the routings in the design. And here is the final, overall evaluations. The top one is the rank clipping to represent Memristor crossbar area reductions, meaning the reduction of the use of the Memristor crossbars. And the second part shows the group connection deletions to show how much we can benefit from the routing area savings. Well, for two networks, we show impact on each individual layers and also the overall impact. For LANet, it's 40 net layers is much bigger than convolutional layers, so it's dominate the overall impact. The ConvNet have more convolutional layers, so this is the average result. So total crossbar area can reduce 13 to 50%, really depends on the network structure. And the routing area is to be 8 to 52%. It's also determined by your application and the data set. So let me again quickly summarize this work. We propose a framework named Group Scissor, which aim to reduce the impact of hardware limitations on RNN-based neuromorphic computing system implementation. We try to extend the scalabilities and map the large neural networks. Rank clipping and group connection deletion methodologies proposed. So the first one is targeted to reduce the area of the crossbar itself, and the second target to reduce the area of the routing part. So again, the limited precision and scalability is, since this is the one student working on this, and this is more like system level approaches to try to solve some lower level device and circuit constraints or limitations. I don't know, any questions?
One question.
Yes.
I heard several recommendation techniques that add extra punishment to penalties. Yeah. I wonder why the back propagation method can learn from this kind of penalty, because this penalty do not have a target relation from the ways.
No. Those are completely like higher levels. Back propagation doesn't apply over here. Okay, let me show you. For example, if you talk about this one is, okay, the assumption here is at the algorithm levels, okay? We try to, apply the situation, apply the constraint penalties on the training schemes. And then through these training schemes, we are able to identify, for instance, the 3-level values over here, okay? And then during the implementations, we program the 3 values to the crossbar arrays. The crossbar array could generate some variations. So the real programming is not like the 3 values. It's essentially will be a small distribution, close to this, and close to this, or even there's some defects to, either side, right? And then the back propagation at the local, since the structure is simple and its functionality is limited, it's kind of local recovery scheme. I don't know if you get. So basically, we use local back propagations, trying to, recover the impact of small deviation over here, but we do not expect back propagation itself can completely handle the entire system variations, or at least not for such kind of complex systems.
So is there another higher level learning?
Yes.
Such as related learning?
Yes. So the system level, the key we try to explain is the system of training structure or algorithm itself have to consider what we have at higher levels and embedded those constraints in the trainings. We couldn't wait till a very later stage when everything has been programmed and then we find, okay, there's so many constraints. And then the delta rule, since it's so simple, it cannot handle everything. Online training couldn't handle everything. Okay. Any other questions? Okay. Well, okay. So next two part, I'm going to talk our latest work on application. There is first. First is the graph processing accelerations. So I guess we all know that graph processing becomes very, very important nowadays. It has a lot of applications. For example, PageRank. PageRank is kind of the web page searchings. So when you're clicking, the web pages, every clicking will generate a link over here, a pointer over here, and each link, will be represented, associated with the numerical values and numbers or values over here. It's essentially represent the importance or the relations, the possibilities from one to another clicks, right? Another example is the breadth first search. It's starting from one point, and during the searching structures, it's first to cover its neighborhood points, and then to expand the searching scopes bigger and bigger. Okay, so one, two more, and each of them will be further extended. All this actually is handled, taken as a graph processing applications, and it's handled by matrix-based operations. And that's why it's kind of natural to introduce R-run crossbar arrays into the graph processing. There are three levels of graph processing solutions, because graph processing is a well-known problem, and many people working on this. So distributed systems in trying to leverage ample computing resources. After-core system essentially is talking about the I/O of the systems, improved I/O, improve the data bandwidth. Domain-specific accelerators, it's kind of for applications we're trying to improve the microarchitectures. Well, the three levels from top to bottoms, conventional computing platforms, there are a lot of works in the areas already. Well, so we also are looking into the graph programming models. So a very common format is vertex-centric programming. So I use this to illustrate the situations. So for vertex-centric programming, we store vertexes. Okay, vertex to vertex is kind of a random accesses. Okay, since they're not correlated. Well, for each vertex, we also store the related edges. For this vertex, for instance, the edge information will be stored in sequence. So this vertex will point to the edge. So within, this edges, this is a local sequential accesses. However, from edge to edge information, globally, the accesses is still random. Usually, both informations will be kind of a large, and it is stored on the massive storage. Well, the global random access on the edges and the vertex, indicating that every update, since the things is random, we actually have to search, find, and replay updated. So the update cost is really, really high. The access cost, in fact, is very, very high. So another approach is edge-centric programming. So in edge-centric programming, as you can see, first we have edge stored. starting from the edge for red first, and then the greenish one, and then blue ones. So corresponding vertex are, can be tracing through the edge over here. So for eccentric scatters, those edges kind of score in a sequential sequence. We can say can be taken as sequential read. Memory locations, edge takes a huge amount of memory space, and usually we can put, for instance, hard disk drives. And for hard disk drives, the sequential read is not that difficult. Vertex, the size is a lot smaller than the edges, so we are able to put it in the main memories. And for memory structures, it can handle random access a lot better than the massive storage. Okay, so in this ways, the read can be taken as sequential accesses, and the write updates can be taken as sequential accesses. So the edge-centric programming is taken as better than the vertex-centric programming. So for the edge-centric gathers, again, to access edges can through the sequential read, and to the vertex destination, it's on memory, so it's random access. Okay. We propose a structure called graph representation. Well, the reason is in graph accesses, matrix itself always sparse. So for the sparse graph matrices, people propose many, compression methodologies. One compression methodology is the compressed sparse column. It's essentially, it has some column pointers, okay, starting from the 0. So it's starting from column 0, okay? So the first pointer is to column 0. And then it says, okay, for the information storage, it's starting from entry zeros. It's looking for the entry over here. It's for the row number and the values of non-zero entries. So 2 and a 1 over here. Okay. And if there's many non-zero entries, for instance, over here, so we got 0, 3, 1, 7, and then the pointer followings will be directed to the entry 4, so on and so forth. This is called the compressed sparse column CSC compression methodology. Similarly, compressed sparse row CSR, taking similar concepts, but it's organized by rows. Or coordinate list, it's using a larger, more entry tables to store the row and column the values, only non-zero entries. Well, such kind of representations save the storage space, but making the computation and searching a lot of complex. The related operation becomes complex. So as you can say, the compressed forms is improve the storage efficiency. Well, with the matrix vector multiplication we talked through the RMs is aimed to improve the computation efficiency. So we propose to use RM and trying to make a trade-off between the storage and the computation. Okay, so let me introduce this. This is the general graph R architectures. Okay, so in graph R architectures, we propose to use RM for both storage and the computation. So as you can see, general architectures, we have some RM memories. It's used for data storage. We also have GEs represent graph entries, many GEs. And each GE is formed by a group of Memristor crossbar arrays. Crossbar arrays have the controller for sure, and it has an driver to drive the crossbar arrays, and sample and hold. It's kind of an activation function nowadays to capture the computation results In output size, if necessary, we can put analog to digitals. Depends on it's a spiking or level-based designs. We have some simple LEs for simple operation or calculations. We also have shift and add units. These both for necessary graph-related calculations. And of course, we have input and output registers to shift the data in and out. It's basically for the data management. All right. This is a little bit, crowded slides. So in this slides, I give one example. Say, okay, how do we use the Memristor crossbar-based graph processing for parallel processing? And an example I take is the page ranking. So for page ranking, let's just take this 4x4 structures here. Page ranking, essentially, we have input page rank vectors, PR0 here. And it's calculated through a weight matrix W with, some, I don't know how can arrow or, offset or previous calculated information over here to create the next page rank. Well, so for this weight matrix, we essentially can map to the 4x4 crossbar arrays, or in sub-array build the bigger crossbars. Okay. In order to operate or calculate this, we can supply the PR0 simultaneous through the input. Okay, so they all supply input. The E is can be stored in an actual row over here, and its input is taken as a 1. Okay, so this is 1/4, 1/4, 1/4, 1/4, like what I give over here, and this is 1. So they all supply simultaneously, and then this functionalities will be calculated directly through the vertical directions. And then we are able to obtain the PR1 in one shot of operation. So this is how do we do the parallel operation. So one thing I want to emphasize over here is this 4x4 doesn't have to be one single Memristor crossbar arrays. It could be a portion of crossbar arrays. And if the portion of this, when we do the operations, we only enable these 4 entries and disable the remaining entries, okay, or 5 entries, disable the remaining entries. It could be very large, then we need partition to, into several sets, and then we use the shift and add units and simple ALUs to consolidate the computation results from different crossbar arrays. That's why we have this in order to handle bigger data set. Well, it can also used for the serial processing. So those are just simple examples. So if you're trying to look for a short path, okay, in short path searching structures, the calculation is kind of starting the source like I0 over here, and then we find what is the short path and then goes to next and next. So in this ways, original matrix is still stored in Memristor crossbar arrays like this. The difference is during the operations, we have to take that one by one, because the short path searching is we go through one levels, find the shortest path, and go to the next levels, and so on and so forth. So as you can see in these illustrations, we have multiple steps. Each of them represent one approx, and so we start from the I0. I couldn't see that by myself. This is 4. 4 is supplied, and the entry 1 is supplied over here. Okay, and this calculate inner results. Okay, and in the inner results, since this is a short path searchings, right? We have to find the minimal values for each Apple entries. So we get those values. Okay. And then for the next steps, we have 3 supplies over here, and then goes to a second, rows, and then we calculate the results, find the normal ones and feedback, and then continue so on and so forth. Okay. So either ways, you can say no matter it's a parallel process or series processes, it can be remapped to the Memristor crossbar arrays, and we are able to realize the functionality. So the design of 2 structures will still remain the same. Well, the key is how do we organize the data? How do we shape the data for different applications? Well, purely I hate to represent the results because it doesn't make much sense. But here we tried architecture level simulations for benchmarks in PageRank applications, breadth first search applications, short pass search applications, and sparse matrix vector applications. So for all of them, generally speaking, compared to CPUs, it's improved the speed quite significantly and also saves a lot of energies. Okay. So all this is, estimations is conducted at the architecture level simulations. I just want to give you a concept over here. Any questions for graph processing? Yeah. So I guess that'd be 5 minutes.
Any questions regarding this part? Okay, if no questions, let's take a 30-minute break, and please come back at 3:15. Thank you.
Thank you.